Every serious performance problem begins with confusion. The code looks clean. The logic is obvious. There's no nested complexity, no wild algorithms, and yet the system slows down under load. This moment is dangerous because most developers respond by reaching for optimization tools instead of questioning their mental model. Let's look at multiple real failure cases where good code runs slow and show that the problem wasn't skill, style, or abstraction. The problem was thinking about code instead of execution. This is the kind of loop no one worries about. It's linear, it's obvious, it's cheap. But on real hardware, this loop can either be blazingly fast or painfully slow depending on one thing, where values live in memory. If the data is contiguous and fits in cache, the CPU flies. If it's fragmented, the CPU spends most of the time waiting. The failure here is assuming that computation dominates cost. On modern systems, memory access dominates execution. When developers say the CPU is slow, they're almost always wrong. The CPU is incredibly fast. What's slow is waiting for data. Arithmetic happens in a few cycles. Memory access can take hundreds. In this failure case, the loop wasn't slow because of math. It was slow because the CPU was idle, waiting for memory. If you don't ask where execution is waiting, you misdiagnose the problem from the start. This code feels expressive, compact, even elegant. But execution-wise, it's a mess. Modern CPUs guess which branch will execute next. When they guess right, performance is great. When they guess wrong, all speculative work is thrown away. Compound data-dependent conditions like this behave unpredictably. The CPU can't learn the path. The failure isn't that the logic is wrong, it's that the logic is surprising to hardware. A single branch isn't expensive, but branches inside loops execute thousands or millions of times. When branch prediction fails inside a hot loop, costs multiply brutally. Developers often focus on algorithmic complexity and forget that execution paths repeat. Small unpredictability becomes massive overhead. This is why performance bugs hide in simple loops instead of complex code. This is good code by most standards. Clear intent, no noise. But what does process actually do? Allocate memory? Call virtual methods? Touch cold data? Branch unpredictably? The abstraction hides execution. When this runs one time, no one notices. When it runs a million times, performance may collapse. The failure isn't abstraction itself. It's losing visibility into what executes inside hot paths. Clean code improves human understanding, not hardware efficiency. The CPU doesn't see clarity. It sees instructions. Abstractions don't remove work. They defer your awareness of it. Performance failures happen when hidden work gets multiplied by scale. If you can't expand a line of code into execution steps in your head, it's dangerous inside a hot path. The code is slow, but the developer trusts the compiler to optimize it away. Compilers are powerful, but they optimize instructions, not design. They can inline functions and reorder operations. They can't fix scattered data, unpredictable branches, or hidden allocations. When execution is chaotic, the compiler runs out of leverage. Failure is outsourcing execution responsibility. Every failure we've seen shares the same root cause. Developers reason in concepts, but the machine executes steps. Memory waits, branch mispredictions, hidden work. None of these appear in source level thinking. Performance problems persist because Refactors change structure, not execution behavior. This is the shift that changes everything. Performance thinking starts when you translate code into execution. Loops become repeated memory access. Conditions become branch predictions. Abstractions become instruction sequences. When you see execution clearly, performance stops being mysterious. You can reason about cost before running the program. Here is the reusable model. First, identify what runs the most. That's where failures hide. Second, expand the code into execution steps. Loads, branches, stores. Third, ask two questions. Where does the CPU wait, and where does it guess? You don't need a profiler to start. Profilers confirm what execution awareness already revealed. Languages evolve. Framework change. Hardware improves. But execution fundamentals stay the same. Memory is slower than computation. Branches cost when unpredictable. Loops multiply costs. This is why performance fundamentals compound over a career while tricks decay. After this, you'll write different code. Fewer surprises. More explicit state. Clearer data access. You'll spot performance problems while writing code, not after users complain. That's real performance literacy. Once you understand how code executes, performance is easy to optimize, not because of tricks, but because you're designing for reality.